The first unit we discussed in this class was applications of integration. And the first application we discussed was how to find areas between curves. So let's sketch the region bounded by y equals 2x and x squared minus 4x and find the area between these two curves. So y equals 2x is a line with slope 2, y-intercept 0. So we rise 2, run 1. So approximately there's your line, y equals 2x. And y equals x squared minus 4x. You can factor out an x, and that tells you that the x-intercept, so this is equal to 0 at x equals 0, and 4. So roughly speaking, your picture will look something like this, and they'll intersect somewhere up there. And you just need to figure out where. So to find the points of intersection, you set the two equations equal to each other. So 2x equals x squared minus 4x. 0 equals x squared minus 6x. Factor out your greatest common factor, and we'll have x times x minus 6. So x equals 0 and 6. Now the area between the curves is given by an integral from 0 to 6 of the upper curve, which is 2x, minus the lower curve, which is x squared minus 4x. So that's the integral from 0 to 6, negative x squared plus 6x dx. And now anti-differentiate, we'll have negative 1/3 x cubed plus 3x squared, evaluated from 0 to 6. And I'll double check that your final question is not such painful arithmetic. But when you work this all out, we end up with 108. Now in this particular example, we just cared about the region where these curves intersected just 2 times. In the next example, we're going to have curves that intersect in between our bounds. So we have the region bounded by sine x, negative cosine x equals 0, and 3 pi over 2. So first let's sketch a graph of sine x. So we only care up until 3 pi over 2, so sketching a graph until 2 pi will be totally sufficient. Okay, so sine begins at 0. By pi over 2, we're at 1. By pi, we're at 0. By 3 pi over 2, we're at negative 1. And by 2 pi, we're back at 0. So there is the graph of the sine function. Now, negative cosine will begin at negative 1, cross at pi over 2. It will be positive 1 by pi, 0 at 3 pi over 2, and back down to negative 1 by 2 pi. And the area that we care about is this part plus that part. So the first thing we have to do is figure out that point of intersection there. So when does sine x equal negative cosine x? And that's at x equals 3 pi quarters and 7 pi quarters. But 7 pi quarters is not in my interval. And so what I'll have to do here is I'll have to find the integral from 0 to 3 pi quarters, and in that case I will do sine minus negative cosine, and then from 3 pi quarters to 3 pi over 2 I'll have to do the opposite thing. So for the first region, we'll have an integral from 0 to 3 pi over 4. So up until 3 pi over 4, the upper curve is sine x. So we'll have sine x minus negative cosine, or plus cosine x, and then plus the area of the other region, so plus the integral from 3 pi quarters to 3 pi over 2. And in that case, we will have negative cosine x minus sine x. Alright, now the antiderivative of sine is negative cosine x plus sine x, evaluated from 0 to 3 pi quarters. That's the first one. Plus the antiderivative of cosine would be negative sine, and then plus cosine x, evaluated from 3 pi quarters to 3 pi over 2. Alright, let's do this first one. So when I plug in 3 pi quarters into cosine, it's negative root 2 over 2. That double negative makes positive root 2 over 2. Sine of 3 pi over 4 is also root 2 over 2. Minus cosine of 0 is 1, so I'll have negative 1 plus 0. So that's from the first one. And the second one, plugging in 3 pi over 2, the sine is negative 1, so I'll have negative 1. Cosine of 3 pi over 2 is 0. And then minus sine of 3 pi quarters is root 2 over 2. And then cosine of 3 pi quarters is negative root 2 over 2. So that gives us root 2 plus 1 plus 1 plus root 2, which is 2 root 2 plus 2. After areas, we discussed finding volumes of solids of revolution. And we had two methods for that, the disk method and the cylindrical shells method. So this one we'll start with the disk method. I won't specify what you have to use on your test, it's totally up to you. So you have to kind of figure out when to use which method and when a certain method is best. So a solid is formed by rotating the area bounded by y equals secant of x. Y equals 1, x equals negative 1, and x equals 1 about the x-axis. Find the volume of the solid. I am going to x-nay the y equals 1 bit because I think that's a typo. So that should have said y equals 0. Okay, y equals secant of x. Now recall that secant is 1 over cosine of x. And cosine is 0 at negative pi halves and pi halves. Roughly speaking, this picture looks something like this. It's not really a parabola, but it sort of has that kind of U shape. So we care about this rotated about the x-axis between negative 1 and 1. And if I slice perpendicular to my axis, each of my slices is going to be a circle, and the area of that slice will be pi r squared. And in this case, r is the distance from my axis of rotation up to that slice, and r is equal to secant of x. Now the volume is found by adding all of these slices up and taking a limit as n goes to infinity, the number of slices. That gives us an integral from negative 1 to 1 of secant of x squared, well, pi secant x squared dx, which is pi times the integral from negative 1 to 1 secant squared x dx. And then you can use symmetry to take twice the integral from 0 to 1. And the antiderivative of secant is tangent. So we'll have 2 pi tangent of 1, which doesn't work out to be a nice number, minus 2 pi tangent of 0. So that's just 2 pi tangent of 1. Sketch the region bounded by the curves y equals cube root of x and x equals 4y. Find the volume when the region is rotated about the line x equals negative 2. Alright, so y equals the cube root of x. So that goes through the point. Let's graph that one in blue. The cube root of x goes through the point 0, 0, 1, 1, and then 8, 2, 3, 4, 5, 6, 7, 8, 2. Also negative 1, negative 1, but okay, roughly speaking, there's cube root of x. Now, x equals 4y is the same thing as y equals 1/4 x. So it starts at the origin, rises 1, runs 4, and from your picture you can see that the points of intersection are at 0, 0 and at 8, 2. So now if we're going to rotate about the line x equals negative 2, got over here, okay, so this curve, you can set it up either way. You can either use cylindrical shells or you can use washers. I will set it up both ways and tell you what the result is once you square everything, and I'll do all the sort of important steps, but the icky, nasty, gory details are a little bit up to you. So now the first thing is, if we are going to use, let's just do the disc method first. That's the first one we learned. It's the disc washer. Okay, we slice perpendicular to our axis of rotation, so that means like this. And my cross sections are circles with holes in them. So the area of my cross section will be pi r out squared minus pi r in squared. And r out, that's the distance from my axis of rotation to the outer curve. That will be 2 plus 4y. And r in, that will be 2 plus y cubed. The distance from here to there is 2, and then the rest of the way to the curve is x, which equals y cubed. And so the volume is the integral. Now because these expressions involve y's, your bounds have to be, your slices begin at y equals 0, and they end at y equals 2 pi times 2 plus 4y, the quantity squared, minus 2 plus y cubed, the quantity squared, dy. So you factor out that pi, you integrate from 0 to 2, and when you expand everything out, you should get 4 plus 16y plus 16y squared minus 4 plus 4y cubed plus y to the 6th dy, which ends up being pi integral 0 to 2 16y plus 16y squared minus 4y cubed minus y to the 6th dy. And after much, much, much painful arithmetic, which I hopefully didn't get wrong, you get 848 pi over 21, counting it not being that evil on your test, okay? So that's if you use the disc or washer method. If you choose to use the shell method, which quite frankly at this point for this particular example I actually prefer that. So we're still rotating about the line x equals negative 2. For the shell method you slice parallel to your axis of rotation, and the, we'll say, volume of a slice is 2 pi r times the height times the thickness, which is delta x. So in this case, r is the distance from the axis of rotation out to that slice, so that will be 2 plus x, and the height of the slice is given by cube root of x minus 1/4 x. And now because your integrals involve x and your slices start at x equals 0, they end at x equals 8, the bounds on your integral must be 0 to 8. So the volume is given by 2 pi, the integral from 0 to 8, r, which is 2 plus x, multiplied by, we'll say x to the 1/3, minus 1/4 x. And the nice thing about this one is I think that the arithmetic is a little bit easier. Not that I would put this problem on a test anyhow, but something similar but with easier numbers might be there. Minus 1/2 x. Now x times x to the 1/3 is x to the 4/3 minus 1/4 x squared. And from there, as long as I made no mistake, you should get the same answer as in the previous question. With a lot of these volume things, the most difficult part is the setup. If you can't get that right, the rest of the work is all for naught. So what also might happen is just to save time, as you might be asked to set up an integral, but not actually asked to solve it. Now we have the base of a solid is the region bounded by y equals e to the x equals 1, y equals 1, and x equals 0. So first let's graph the region. And find the volume if the cross-sections perpendicular to the x-axis are squares. So e to the x goes through the point 0, 1. All right, x equals 1. Got that vertical line. Horizontal line at y equals 1. And I guess we don't really even need the x equals 0 bound, but okay, so x equals 1, y equals 1. Cross sections perpendicular to the x-axis, so slicing this way, are squares. So now in this case we do not have a pi. The area of the cross section is just side squared. So that's the base, and squares are coming up out of the page at us. Now the length of a side will be e to the x minus 1. And the volume is found by adding all the slices up, or integrating from 0 to 1. E to the x minus 1 squared dx. Now, if we multiply e to the x minus 1 by itself, the only slightly tricky thing is what is e to the x times e to the x. And recalling your rules for exponents that you learned an awfully long time ago, that should make e to the 2x. Because there's a common base, the exponents add. And then we'll have minus 2 e to the x plus 1. Now the antiderivative of e to the 2x is e to the 2x 1/2 minus 2 e to the x plus x, evaluated from 0 to 1. So that will be 1/2 e squared minus 2e plus 1. And be careful with 0, because plugging in 0 does not necessarily yield 0. E to the 0 is 1, so we'll have 1/2 minus 2 plus 0. So that's 1/2 e squared minus 2e, and then we'll have plus 5 over 2. This 1 plus that 2 makes 3. 3 is 6/2 minus 1/2 is 5/2. Using the method of cylindrical shells, find the volume obtained by rotating y equals x squared plus 4, y equals 0, x equals 0, and x equals 4 about the y-axis. A graph of the region is shown below. Well, there is a graph of that region on your note sheet. Looks something like this. There's the curve, we've got a vertical line, and we're going to rotate about the y-axis. So we will slice this way. Okay, so remember that the cylindrical shells is 2 pi r times the height delta x. So in this case, the radius is just equal to x, and the height is just the root of x squared plus 4. So the volume will be given by 2 pi integral from 0 to 4 x times the root of x squared plus 4 dx. And to integrate this, you're going to need to do a u substitution. You'll let u equal x squared plus 4. Du is equal to 2x dx. So we'll have 2 pi times 1/2, and then a u to the 1/2 du. And you also have to change your bounds. If x equals 0, plugging that into x squared plus 4, we get that u is equal to 4. And if x is equal to 4, u is 20. And now it's not so bad. So we have pi. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3, evaluated from 4 to 20. So that's 2 pi over 3 times 20 to the 3/2 minus 4 to the 3/2. And I apologize for the slight ickiness of these numbers. Now 20 to the 3/2 will end up being root 20 3 times, so root 20, root 20, root 20, which will make 20 root 20, which will make 20 is 4 times 5, root that 4 to make 40 root 5. So we have 2 pi over 3 times 40 root 5, and 4 to the 3/2, the root of 4 is 2, 2 cubed is 8. Now sketch the region bounded by the curves y equals x squared minus 6x plus 10 and x squared plus 6x minus 6. So we have two parabolas here, a sort of right side up parabola and upside down parabola. Let's start by finding the points of intersection. So x squared minus 6x plus 10 will equal negative x squared plus 6x minus 6. So we get 2x squared minus 6x plus 16 equals 0. Oh, not minus 6x, minus 12x. That was all of a sudden not going to factor. Divide by 2, we get x squared minus 6x plus 8 equals 0, which factors into x minus 4, x minus 2, and we get x equals 4 and 2. Now, if we input 2 into the first equation, we get 4 minus 12 plus 10. So that looks to me like 2. The next point is there and then there. So roughly speaking, that parabola looks like this. The other equation, well, we know that they intersect at 4 and 2, so it has to go there. When you input 3, you end up getting 3. So there's the negative parabola. And we're going to rotate about the line x equals 5. I had a really good talent for making extremely tedious problems for this, so we're just going to set up this integral. We're not going to solve it. I did, and you can look at the work, but it's evil. So the volume will equal 2 pi integral. Now the slices here, because we're going to do cylindrical shells, they're parallel to your axis of rotation. They begin at x equals 2, they end at x equals 4. Now the one slightly tricky thing is the radius, so you need that distance. So the total distance from the x-axis over to the line is 5. The distance, that little blue distance, is x, making this distance 5 minus x. So your radius is 5 minus x. And the height of the curve is found by taking the upper equation minus the lower equation. And the upper equation is this negative x squared plus 6x minus 6. So negative x squared minus x squared makes negative 2x squared. 6x minus negative 6x makes positive 12x. And negative 6 minus 10 will make negative 16. And then you have to distribute that out, anti-differentiate, ugliness, and much suffering. And I ended up with 32 pi thirds. But like I've said before, I'll make sure that the questions on your final actually work out reasonably nicely and don't involve super tedious arithmetic before I give them to you. The next application we had was how to find the length of a curve. So the arc length formula L is the integral from a to b root 1 plus f prime of x squared dx. So I have ln of cosine x between x equals 0 and pi 6. So y prime is 1 over cosine x multiplied by negative sine x, because of the chain rule. So that's the same thing as negative tangent of x. So the length of this curve is given as an integral from 0 to pi 6, the root of 1 plus tangent squared x dx. And if you remember your Pythagorean identities, 1 plus tangent squared x, that is secant squared x. So you root that and you get the integral from 0 to pi 6 of secant of x dx. And it's a formula that you're not supposed to necessarily have memorized, but the antiderivative of secant is the natural log of the absolute value of secant x plus tan x. With these questions, it's really difficult to make one that works out really nicely from 0 to pi 6. So we have ln of secant of pi 6. So that's 1 over root 3 over 2 plus tangent of pi 6, which is tangent is sine over cosine, so 1/2 over root 3 over 2 minus ln, well, secant of 0 is 1, tangent of 0 is 0. So that gives me ln of 2 over root 3 plus 1 over root 3, which is ln of 3 over root 3. And 3 over root 3 is the same as root 3. And in addition to arc length, we also found surface areas when rotating a region about some kind of axis. So we want to find the surface area of the surface obtained by rotating y equals 1/2 x squared between x equals 1 and 3 about the x-axis. So that's taking this parabola, kind of a stretched out parabola, between 1 and 3 and going about the x-axis and finding the volume of the rotated portion, so that the surface area, sorry, of the rotated portion. And the way that I remember this formula is that, so you'll have to have the radius, so how big the thing spinning is, so 2 pi r, in this case r is equal to x, multiplied by the length of like a little curve, which is given by the same portion as like the arc length formula. So 1 plus f prime of x squared dx. So my surface area is 2 pi, integral from 1 to 3, x times the root 1 plus x squared dx. The derivative of 1/2 x squared is just y prime equals x. That was kind of on purpose, so it would work out a little bit nicely. Now we're going to once again do a u substitution. So let u equal 1 plus x squared. Du is 2x dx. Half du equals x dx. And if x equals 1, u is equal to 2. And if x equals 3, u is equal to 10. So this becomes 2 pi integral from 2 to 10 u to the 1/2 du. So that's 2 pi u to the 3/2, 2/3, 2 to 10. So 4 pi over 3. Now 10 to the 3/2 will be 10 root 10 minus 2 root 10, or 2 root 2, sorry. So 10 root 10 minus 2 root 2. Next, we discussed work. So remember that work is defined as force times distance. Notice that there's no time component. You've got to not think about work as how hard something is, but as the specific definition of force times distance. So which of the following scenarios requires more work? So A, lifting a 10-pound box of books 3 feet off the ground. So for part A, the work will equal force times distance, and the force is 10 pounds, the distance is 3, so the total work required there is 30 foot-pounds. Now for part B, holding a 30-pound box of books 2 feet in the air is a force of 30, but it's not moved, so the distance is 0. So in there, the work is 0 foot-pounds. So as a result, part B or part A requires more work. Now, one example of work that comes up often in physics is an example of a spring. And so a force of 25 pounds is required to hold the spring stretched 18 inches beyond its natural length. How much work is done in stretching the spring an additional 12 inches? Give your answer in foot-pounds. The hint is to use Hooke's law, which states the force required to hold the spring x feet beyond its natural length is f of x equals kx, provided x is not too large. So first, let's convert 18 inches into feet. So 18 inches is 1.5 feet, so that would be 1.5 or 3/2 feet. Alright, now we have to find the k in that f of x equation. We know that f of 3/2 is equal to 25. So 25 equals 3/2x, or 3/2 times k. The x is 3/2. So k will be equal to 50 thirds. And I have f of x equals 50/3 times x. Now the total work here, so this is the force, so you have on the y-axis you have the force equation, who's measured in, I guess that must be pounds, and you have the x, which is measured in feet. To get foot-pounds you have to integrate, and we want to say moving an additional 12 inches, so that would be from 3/2 to 2.5, which would be 5/2. 50 thirds x dx. So that's 50 thirds times x squared over 2, evaluated from 3/2 to 5/2. Now 50 thirds divided by 2 would be 25 thirds. 5/2 squared is 25 quarters minus 9 quarters. It will be 25/3. It'd be nice if I could actually write 25. 25/3. So 25 minus 9 is 16 quarters, which would be 4. So that will be 100/3 foot-pounds of work. The point is that the work is greater the farther and farther and farther you stretch that spring. And the final application is centroids and centers of mass. So first, we're going to consider the region bounded by y equals a sine of 2x, y equals 0, x equals 0, and x equals pi halves. We're going to sketch the region and find the area bounded by the two curves, and then we're going to find the center of mass of the region. So sine of 2x is a sine curve kind of sped up, so its period is pi instead of 2 pi. Starts at 0, it's 1 at pi quarters, back down to 0. So we care about this region. And we're going to find the balancing point, like the middle x and the middle y. But first we need the area. So the area is an integral from 0 to pi over 2 sine 2x. Officially, if you had another curve, you'd take away the other curve, but we don't. The other curve is just 0 dx. So that's negative 1/2 cosine of 2x, 0 to pi over 2. So that's negative 1/2 cosine of pi plus 1/2 cosine of 0. Cosine of pi is negative 1, making this a half plus a half, so that area is actually 1. Now, the way to find the center x, or the x bar, is to do 1 over a, the integral from a to b, x times f of x minus g of x. Now, because of the symmetry that you can see in the previous picture, I think it's pretty obvious that that x bar probably should be at pi quarters. Let's just verify it. And in this case, because my lower curve is just the x-axis, g of x is 0. So we'll have 1 over 1, the integral from 0 to pi over 2, x times sine of 2x dx. And we haven't technically reviewed it yet, but this is an integral that you have to do by parts. So we'll let u equal x, du is dx, dv is sine 2x dx, and v would be negative 1/2 cosine 2x. So we'll have negative 1/2 x, that's uv, from those uv minus integral v du, so negative 1/2 x cosine of 2x, and because this no longer has an integral, we have to evaluate it from 0 to pi over 2, minus, which will become plus because of the double negative, plus the integral from 0 to pi over 2 of 1/2 cosine of 2x dx. So now, in that first portion, plugging in pi over 2, I'll have negative pi over 4 times cosine of pi plus, well, just 0 because of the x there multiplied by the cosine of stuff. And then I'll have plus 1/2 times 1/2 sine of 2x, evaluated from 0 to pi over 2. So since cosine of pi is negative 1, I have pi quarters plus 0 plus 1/4 times, now sine of 2 times pi over 2, so pi, I get the sine of pi, which is 0, minus 0. So as we thought, the center x coordinate is x equals pi quarters. Now let's find the y coordinate. Y bar is 1 over a, integral from a to b, 1/2 f of x squared minus g of x squared dx. So that will be 1 over 2, because my area is just 1, the integral from 0 to pi over 2 sine squared, sine of 2x, the quantity squared. So that's the same thing as 1/2, the integral from 0 to pi over 2. Now sine squared of 2x, we can use the half angle identities to change that into 1/2 times 1 minus cosine of 4x. So that will be 1/4 times the integral from 0 to pi over 2, 1 minus cosine of 4x dx. So 1/4 x minus 1/4 sine 4x, evaluated from 0 to pi halves. So that will give me 1/4 times pi over 2 minus, let's think that will be sine of 2 pi, which is 0, minus 1/4 times, both those next terms will be 0. So the y bar is pi over 8. So in a nutshell, that's basically the content of the first unit, or also all the stuff that was sort of on your first exam.